In integral calculus, elliptic integrals originally arose in connection with the problem of giving the arc length of an ellipse. They were first studied by Giulio, Fagnano and Leonhard. Euler. Modern mathematics defines an elliptic integral as any function f which can be expressed in the form where r is a rational function of its two arguments. P is a polynomial of degree 3 or 4 with no repeated roots, and c is a constant. In general, integrals in this form cannot be expressed in terms of elementary functions. Exceptions to this general rule are when p has repeated roots, or when r contains no odd powers of y. However, with the appropriate reduction formula, every elliptic integral can be brought into a form that involves integrals over rational functions and the three legendary canonical forms. Besides the legendary form given below, the elliptic integrals may also be expressed in Carlson symmetric form. Additional insight into the theory of the elliptic integral may be gained through the study of the Schwarz-Christoffel mapping. Historically, elliptic functions were discovered as inverse functions of elliptic integrals. Argument notation. Incomplete elliptic integrals are functions of two arguments. Complete elliptic integrals are functions of a single argument. These arguments are expressed in a variety of different but equivalent ways. Most texts adhere to a canonical naming scheme, using the following naming conventions. For expressing one argument: alpha, the modular angle; k equals sin alpha, the elliptic modulus or eccentricity; m equals k2 equals sin 2 alpha, the parameter. Each of the above three quantities is completely determined by any of the others. Thus, they can be used interchangeably. The other argument can likewise be expressed as phi, the amplitude, or as x or u, where x equals sin phi equals SNU and Sn is one of the Jacobian elliptic functions. Specifying the value of any one of these quantities determines the others. Note that u also depends on m. Some additional relationships involving u include the latter is sometimes called the delta amplitude and written as delta equals dnu. Sometimes the literature also refers to the complementary parameter, the complementary modulus, or the complementary modular angle. These are further defined in the article on quarter periods. Incomplete elliptic integral of the first kind. The incomplete elliptic integral of the first kind f is defined as this is the trigonometric form of the integral. Substituting, one obtains Jacobi's form. Equivalently, in terms of the amplitude and modular angle one has. In this notation, the use of a vertical bar as delimiter indicates that the argument following it is the parameter, while the backslash indicates that it is the modular angle. The use of a semicolon implies that the argument preceding it is the sign of the amplitude. This potentially confusing use of different argument delimiters is traditional in elliptic integrals, and much of the notation is compatible with that used in the reference book by Abramowitz and Stegun and that used in the integral tables by Graj10 and Rajik, with one has. Thus, the Jacobian elliptic functions are inverses to the elliptic integrals. Notational variants. There are still other conventions for the notation of elliptic integrals employed in the literature. The notation with interchanged arguments, f, is often encountered, and similarly for the integral of the second kind. Abramowitz and Stegun substitute the integral of the first kind, f, for the argument phi in the definition of the integrals of the second and third kinds, unless this argument is followed by a backslash, i.e., k2 free. Moreover, the complete integrals employ the parameter k2 as argument in place of the modulus k, i.e., k rather than k, and the integral of the third kind defined by Graj10 and Rajik pi puts the amplitude phi first and not the characteristic n. Thus one must be careful with the notation when using these functions, because various reputable references and software packages use different conventions in the definitions of the elliptic functions. For example, some references, and Wolfram's Mathematica software and Wolfram Alpha, Define the complete elliptic integral of the first kind in terms of the parameter m, instead of the elliptic modulus k. Incomplete elliptic integral of the second kind. The incomplete elliptic integral of the second kind D in trigonometric form is substituting. One obtains Jacobi's form. Equivalently, in terms of the amplitude and modular angle. Relations with the Jacobi elliptic functions include the meridian arc length from the equator to latitude is written in terms of E, where A is the semi-major axis, and E is the eccentricity. Incomplete elliptic integral of the third kind. The incomplete elliptic integral of the third kind pi is, or the number n is called the characteristic and can take on any value, independently of the other arguments. Note though that the value is infinite, for any m. A relation with the Jacobian elliptic functions is the meridian arc length from the equator to latitude is also related to a special case of pi. Complete elliptic integral of the first kind. Elliptic integrals are said to be complete when the amplitude phi equals pi 2 and therefore x equals 1. The complete elliptic integral of the first kind k may thus be defined as or more compactly in terms of the incomplete integral of the first kind as. It can be expressed as a power series where Pn is the Legendre polynomial, which is equivalent to where n denotes the semifactorial. In terms of the Gauss hypergeometric function, the complete elliptic integral of the first kind can be expressed as the complete elliptic integral of the first kind is sometimes called the quarter period. It can most efficiently be computed in terms of the arithmetic geometric mean. Special values relation to Jacobi theta function. The relation to Jacobi's theta function is given by where the norm q is asymptotic expressions. This approximation has a relative precision better than 3 times 10⁻⁴ for chi less than 1/2. Keeping only the first two terms is correct to 0.01 precision for chi less than 1/2. Differential equation. The differential equation for the elliptic integral of the first kind as a second solution to this equation is. This solution satisfies the relation. Complete elliptic integral of the second kind. The complete elliptic integral of the second kind is defined as or more compactly in terms of the incomplete integral of the second kind as for an ellipse with semi-major axis and semi-minor axis and eccentricity. The complete elliptic integral of the second kind is equal to 1/4 of the circumference of the ellipse measured in units of the semi-major axis. In other words, the complete elliptic integral of the second kind can be expressed as a power series which is equivalent to in terms of the Gauss hypergeometric function. The complete elliptic integral of the second kind can be expressed as the complete elliptic integral of the second kind can be very efficiently computed by a modification of the arithmetic geometric mean. Special values derivative and differential equation. A second solution to this equation is complete elliptic integral of the third kind. The complete elliptic integral of the third kind pi can be defined as. Note that sometimes the elliptic integral of the third kind is defined with an inverse sign for the characteristic n. The complete elliptic integral of the third kind can be very efficiently computed by a generalization of the arithmetic geometric mean. Partial derivatives. Functional relations. Legendre's relation.